Just a reminder, this week, obviously, we don't have class on Thursday because of Thanksgiving. So that'll leave us one class out, but that's perfectly fine. We'll pick back up when we jump in. The one thing I always say though at Thanksgiving, we're going to still have homework that's due. All right, so there's still homework due Friday. This vector stuff will be due Friday, and depending on how far we get, some other stuff too. All right, so don't forget about the Friday homework, even though there is no class on Thursday. All right, so this section we're going to look at vectors. A vector is an object in space that gives magnitude and direction. So it's going to give us a length and a direction. Okay, so a lot of times these are represented by like arrows when you draw it in 2 dimensions. And because we have both direction and magnitude, geometrically, it's a ray that's starting at some point and ending at some other point. We call the starting point the initial point and the ending point the terminal point, right? So we got an initial and a terminal point. Now we'll very quickly translate everything into standard form. The standard form of a vector, well, one of the standard forms is going to be this. It's going to be how far we traveled in the x direction, comma, how far we traveled in the y direction. And then we put these sort of vector brackets around that. So it kind of looks like an ordered pair, just with vector brackets. So how far we traveled in x, comma, how far we traveled in y. Right. This is called the standard position vector. If we think of a vector starting at one point, ending at another, the standard form basically tells you how far in the x direction, how far in the y direction, and therefore it's like that vector is starting at the origin, like where its initial point is the origin, right? That's the standard position vector, okay? Now there's lots of different notations for vectors. One of the notations is where we have a line across the top. We can write a vector starting at point A and ending at point B as AB with an arrow on top of it pointing to the right. Okay. Since the A is on the left-hand side, that means we're starting at A. B on the right-hand side means we're ending at B. Oftentimes, once we get into this stuff, we'll use a single letter as a vector rather than from A to B, especially if we're using the standard position vector. We'll just call it a single letter. And common letters that people use for vectors are U, V, and W. In books, what happens is they tend to either use bold font for their vectors, or they use that arrow on top of the letter for their vectors. Bold font is kind of hard to write on the board, but it's easier to see, well, easy to see in a book. So a lot of times when they type it in the book, it's bold font. The arrow on top of a letter oftentimes is used more when you hand write things because it's really hard to write in bold. If that makes sense. So you'll see both of those fonts for various vectors. Again, a lot of times when the vectors are in standard position, we see that. Okay. Now, in this class, we're going to use that standard vector brackets, that vector notation that I just saw, or that we just saw, I should say. But also, in other scenarios, you can use just a list of numbers. You can either write that vertically or horizontally. And if you write the list of numbers, as you see there, either vertically or horizontally, that's also, vectors. And we can do the same operations, whatever notation we use. Okay. We'll use that vector notation in this class. So let's do some examples of this. We're going to find the standard position of the vector with initial point given and terminal point given. So if the initial point where the vector starts is 4, 5, and the ending point is 8, 13, or the initial point is -2, -3, and the terminal point is -7, 8, or the initial point is -5, 0, and the terminal point is 1, 12. We want to find the standard position vector in each of those cases. All right. All right. So, standard position. I'll do this in 2 steps. We got to figure out the change in X and then the change in Y. Be careful about which way you subtract. When you subtract, you got to do the terminal value minus the initial value. Does that make sense? Terminal minus initial. So in this case, 8 minus 4 for the change in the X values, and 13 minus 5 as the change in the Y values. In this case, that's the standard position vector for 8. And what that means is that if we started at 4, 5, we would have went right 4 units and then up 8 units. And my vector would have looked something like that. That makes sense. So we're going right and up. Right 4, up 8. Make sense? That's the vector for 8. Same thing here, just be careful. -7 minus -2. Change in the X values. 8 minus -3. Change in the Y values. Same thing here. 1 minus -5. 12 minus 0. So we get 6/12. So those are the three vectors in standard position. Four, 8, -5, 11, 6, 12. Make sure you're subtracting terminal minus initial to get the right direction. And if you're ever in doubt, just think about how this is going to work. For starting at 4, 5 and ending up at 8, 13, you draw that arrow. You're moving to the right and up. So you should be moving positive X direction and positive Y direction. That makes sense. So for this one, on this one, we would have started at -2, -3, and then went to -7, 8. And draw that pretty well. -2, -3. So we would have went more left, but up. Notice we're moving left and then up. So we got a negative X direction, but positive Y direction. We get that on this second one. So when in doubt, just draw that arrow and hopefully it makes sense in what direction you're going. Now, one important vector that we're going to look at is the is the zero vector. We will look at unit vectors as well, but the zero vector can be denoted by either just a 0 with a vector line on top, vector arrow on top, or it can be denoted as a bold-faced 0. But it's the vector which contains all zeros. So every entry is the number 0. Other key vectors are vectors I and J. I as a vector is the standard position vector 1, 0. J as a vector is the standard position vector 0, 1. And any other vector can be built from I's and J's. That's why I and J is important. By the way, if you think about what those vectors are, in terms of the XY axis, the 0 vector is the one that just stays at the origin. Okay. I goes out 1 unit along the x-axis. That's the vector I. J goes out 1 unit along the y-axis. Does that make sense? So that's what I and J are doing, and the 0 vector is the only one that stays at the origin. Now, like I said, vectors give length and give magnitude and direction. Okay. The magnitude is going to be the length of the vector, And the direction in R2 will be the angle from the x-axis. Just like with polar coordinates, we had angle from the x-axis, so we can find the direction that way. Okay. So if magnitude is the distance or length of a vector, then we can take that vector, since A tells us how far we go in the x direction, B tells us how far we go in the y direction, and the magnitude or the length of the vector is going to simply be a hypotenuse of a triangle. And so we can find that length by taking the positive square root of a squared plus b squared. Does everybody understand what I'm saying there? We'll get into I'll draw some examples in a moment. And then, like I said, direction is going to be angle from the x-axis with the standard position vectors. So with the standard position vector, the angle from the x-axis, we've done this before, as tangent of theta is equal to b over a. Depending on what quadrant it is, the angle's in or the vector's in, theta might be the inverse tangent of b over a, but it also could be the inverse tangent plus pi of b over a. You know what I'm saying? Pi plus the inverse tangent. We've dealt with that before too. So let's take a standard position vector like 4, 3, and let's find magnitude and direction. And then we'll do the same thing for -2, 7. And then we'll do the same thing for the 0 vector. All right, so let's take 4, 3. We'll try to find the magnitude or the length. We denote the length or magnitude of 4, 3 of a vector by doing 2 lines on each. This is a universal symbol for a metric, a measuring length, way to measure length, way to measure anything. So the 2 slash on either side, hopefully you saw that on the slide, which is just the positive square root of 4 squared plus 3 squared. We end up with 25 in this case. So underneath the square root. So the magnitude of this vector is 5. Or the length of that vector is 5. And again, all we're doing is we're saying we're going out 4 and up 3. So we're getting that vector. We're trying to find the length. And we're saying, well, if I know the base and height's 3, length's 4, this is the right triangle. So a squared plus b squared is equal to c squared, Pythagorean theorem. that means the C of the hypotenuse of that right triangle is the square root of A squared plus B squared. That's where that formula is coming from. Okay. So that's where the formula is coming from. That's what we always end up doing. And then the direction tangent of theta is equal to the B over A, which is the Y piece over the X piece. That's exactly what we did with tangent earlier. Tangent was Y over X on a triangle. Think of opposite over adjacent. So 3 over 4. We're in quadrant 1. So that means the theta is going to be the inverse tangent of 3/4, or the arc tangent of 3/4. Which is about 0.6435. That is radians. All right. I went out to more decimal places on the homework. I think you'll have to go out to 2, but I just want to go out a little bit further so you see what we get. Is that all right? So magnitude and direction of a standard position vector. Let's do the magnitude or the length of this vector. We'll take the square root of -2 squared plus 7 squared. That's the square root of 53, which is not a super nice number. It's fine. It's irrational. No big deal. Everybody's here, I'm getting 53 from. This is 4. This is 49. Add them together, you get 53. So square root of 53 is about 7.28. So the magnitude of that vector is 7.28. Now the direction of this vector tangent of theta should be equal to, in this case, 7 over -2 y over x, in other words. But on this one, it's in quadrant 2. This vector, -2, 7, is in quadrant 2. And my tangent inverse is only going to give me things in quadrant 4 or quadrant 1. So we're going to add pi to get into quadrant 2. So theta is equal to pi plus the inverse tangent of 7 over -2. Again, we did a lot of that earlier. That's about 1.85 radians. So about 1.85 radians. So anytime we're in quadrant 2 or quadrant 3, we add pi whenever my calculator gives out for inverse tangent. If I'm in quadrant 1 or quadrant 4, my calculator will give me something out in quadrant 1 and quadrant 4. So I don't have to add pi to any of that. Now let's look at the length of the zero vector. Length of the zero vector is, as you probably guessed, 0. The zero vector is the only vector of length 0. This is the vector that just stays at the origin in standard position. And if you think about direction, well, what would we do? We'd start out with tangent of theta is equal to 0 over 0, but 0 over 0 is undefined. So there's no theta I can plug in to get 0 over 0, because that's an undefined scenario. So we say that the zero vector has no direction. That makes sense. Now, I do want to add one little caveat because I don't want you to think the reason for that zero vector having no direction is just the 0 in the x value. If you take something like 0, 8, the length of that notice what's going to happen. We're going to get 0 squared plus 8 squared underneath the square root. That's just 8 squared underneath the square root. If I take the square root of 8 squared, I just get back 8. So length of 0, 8 is 8. That should have been fairly obvious. It's going straight up the y-axis. Now the direction, technically we have tangent of theta is equal to 8 divided by 0. This is undefined in a slightly different way. We have an actual value on top divided by 0. When you do the calculus version of this, what you'll see is that we're starting here and you take a limit, and as x goes to 0, the limit goes to infinity. So we're pointing straight up. Since we're pointing straight up, the angle is actually just pi over 2. Everybody get that? The angle on this is pi over 2. It really is not this one you can't do with a calculator necessarily, but you can do with just basic logic. Right? So your calculator doesn't help you a lot on that one, but basic logic says we're pointing straight up, so we are at angle pi over 2. And this is what happens, this is how you get undefined if you take a tangent of pi over 2. then you're dividing by 0 in the sine over cosine version of that. Cosine of pi over 2 is 0. That throws us off.
What if it was 8-0 instead of 0-8?
Oh, then you can have 0 over 8, and that's perfectly fine to do an inverse tangent with. Yep. And you'll get an angle of 0. It'll be right along the x-axis. All right, I want you to try 2 more on your own. Find the magnitude / length and direction of these 2 angles. Or these 2 vectors, excuse me. We'll find the angles. Oh, then I as well. Sorry, didn't see the I there. So these 3 vectors. -5, -1, -0.5. Put 3 over 2, and then I. And round things to a couple of decimal places with all your rounding. All right, so let's take a look at this. Each of these, we're going to take -5 squared plus -1 squared all under the square root, which is the square root of 26 when I calculate that out, which is about 5.099 or 5.10 if I round it to 2 decimal places. The direction here I get by doing a tan of the angle is equal to -1 over -5. We're in quadrant 3. We're negative, x and y values, so we're in quadrant 3. And that means theta is going to be pi plus the inverse tangent of -1 over -5. When you do that, you end up with about 3.34 radians as your angle. That should make sense because 3.34 is a little above pi, right? Pi is 3.14, so we are in the third quadrant in that scenario. For this one, when you take the square root of -1/2 squared plus √3 over 2 squared, I get 1/4 plus 3/4. When you add up 1/4 plus 3/4, you get 1. So that's the square root of 1, which is a 1. By the way, we probably already knew that because when we dealt with trig stuff, this was one of the points on the unit circle. 1/2 comma √3 over 2, or -1/2 comma √3 over 2. That was a nice point on the unit circle, right? So if it's on the unit circle, starting at the origin, that's a length of 1. Radius is 1. The direction, again, tangent of theta is going to be √3 over 2 divided by -1/2. The 2's in that denominator will cancel out, so I'll write that. This is in quadrant 2. So once again, I'll have to add pi to whatever my calculator gives me out as a result. With the inverse tangent. So I do inverse tangent of a negative square root of 3 and then add pi to that. That's an angle of about 2.09 radians. By the way, if you did this in exact mode, if you look this up on the unit circle, it would be 4 pi over 6 radians or 2 pi over 3 radians if you did that in exact mode. Okay. I'm getting that from the unit circle, right? And knowing what the decimal version is. So 2 pi over 3 radians, or about 2.09 radians. length of I. Remember, I is 1, 0. So the length is 1. That's one of the nice things about having vectors where you only have one non-zero entry, is that the length is just the absolute value of that entry. All right. So, like in our previous one we had earlier, we had 0, 8, which had a length of 8. Here we have 1, 0, which has a length of 1. If I started with -4, 0, length would be 4. Pretty straightforward, right? If all of the other entries are 0, then the length of the vector is just the one non-zero entry in absolute value. Direction. Tangent of theta is 0/1. This, we kind of already know where it's at, but still you could do the theta. This is, by the way, this vector is along the x-axis between quadrants 4 and 1. So between quadrants 4 and 1. So theta can be given to me by taking the inverse tangent. That's 0. Which gives me 0. Okay. So theta is equal to 0. We kind of already knew that because it's along the x-axis. We know that angle 0 is the one pointing right along the x-axis. All right. Now I want to mention this before we move on because it's going to come back later on in the section. I want you to notice that I and -1/2 comma √3/2 were both of length 1. Those are special types of vectors that we call unit vectors. Vectors of length 1 are called unit vectors. We'll deal with those in a little bit, but I just wanted to point out that those two having length 1 make them special types of vectors. Okay. My other vectors like 0, 8, or like -5, -1, those are fine, just not unit vectors. Okay. So now we know how to calculate length and direction, or magnitude and direction of lots of different vectors. Once we calculate length and direction, then we're going to start using vectors, adding them up, subtracting them. Manipulating them in other ways as well. So first off, let's talk about adding and subtracting two vectors. If I take two vectors and I want to add them, I just do it component-wise. I add the x parts together, I add the y parts together. If I want to subtract them, I do the same thing. I do it component-wise. I put the x parts together, but subtract, put the y parts together, and subtract. So for instance, if I wanted to do a 2, 3, and then add 1, 4, for example, what that would give me is the vector 3, 7. 1 and 2 had to give me 3. 3 and 4, add, give me 7. One way of viewing this is geometrically, if I take the vector 2, 3, let me write that in a different color. 2, 3, it's a vector pointing in this direction. Hitting that point. When I add 1, 4 to that, basically I think of starting at this point where I ended, and then moving over 1 unit to the right, and then in this case 4 units up. So it's like I'm tacking on the other vector that way. Does that make sense? So these two vectors combined give me the vector 3, 7. Does that make sense? Because if you go in that direction and that length, and then add an additional that direction, that length, you've went total of that other direction, that length. They follow. So we're just tacking on vectors back to back. And you can do the same thing with subtraction. All you really need to know is that, let me do it this way. If you put a negative sign in front of this vector, that's like a -2, -3. So subtracting is like going in the opposite direction. So this was 2, 3. -2, -3. Put that red. It's just going to be that same vector flipped 180 degrees. Does that make sense? Okay. So that's what's happening geometrically. Okay. One other operation that we're going to use, it's called scalar multiplication. When you multiply a vector by a scalar, you just multiply each component by that value. Okay, so usually this is a real number. And if I multiply, for instance, 2, 3 by the number 3, I should get 6, 9. Oops. Okay. Geometrically, what's going on there is that you're just taking your vector 2, 3, which used to be right here, and you're stretching it out by a factor of 3. So you're stretching it out, and now you're going to do that once, do that twice, do that 3 times, back to back. Okay, so you're going the same direction, just stretched out longer. Stretched out by a factor of 3. And if I stretched out by a factor of 2.5, then I, stretch it out by a factor of 2.5. If I stretched it out by a factor of pi, I stretch it out by a factor of pi. So it's going in the same direction, but just longer or shorter. If I shrunk it by a factor of 1/2, multiplied by 1/2, then it gets shorter. Multiplying by 3 get made it long. Okay. So that's what's happening with scalar multiplication. These things are pretty straightforward to do in terms of the calculations. So why don't you try example 4 on your own? Calculate these, add 2 vectors, subtract 2 vectors, and then do scalar multiplication with addition of 2 vectors. All right, so let's do these 3 problems. So with vector addition, we just add component wise. So as long as we don't mess up our arithmetic, we get the right value. 3 plus 8, 11. 7 plus 2 is 9. So we get the vector 11, 9. Okay. When you subtract, we subtract -2 minus 4, that's a -6. 6 minus 7 is a -1 or -1. So we get the vector -6 comma -1. When I throw in some scalar multiplication with that, I'm going to distribute the 15 into both parts. That's going to be 30 comma -15. Then I distribute this 5 into both parts. That's going to be a -45 comma 15. When I add those 2 things up, 30 minus 45 or 30 plus a -45 gives me a -15. And then -15 plus 15 gives me 0. So I get -15, 0 as the result here. Good. You can do this with notation as well. rather than the actual vectors themselves, I could give names to the vectors. I could say that vector V is 8, 6, and vector W is 5, -4. And then do operations on these as well. Go ahead and try these on your own. All right, so let's do this. Essentially, I just substitute out the V for what it stands for. I take 8, 6 plus 2 times 5, -4. Sometimes people do this all in one step. Or they'll write, well, that's just 8, 6. And then they'll multiply the 2 in as they put it in, which gives me 10, -8. Combining, I get 18, -2. And that would be my final answer. Okay. Be careful on order. Sometimes I'll mix up the order. This starts with the W first. So we go 3 times the 5, -4, minus 10 times the 8, 6. We get 15, -12 when I multiply the 3 in. What I would probably do is I'd multiply in a -10 and then put a plus sign out here. You could also multiply the +10 and leave the minus sign there. Doesn't, either way is fine, but I generally distribute the negative sign with it. So we get -80, -60. Combining those, we get a -65, comma, -72. But no, 0v is 0. It's a 0 vector, right? So 0 times anything, any real number, I should say, is 0. So we get the 0 vector. So 0 times any vector is the 0 vector. Okay. Now, what we just did there was we took what's called a linear combination of the V and the W. A linear combination of two vectors is just, can I add those vectors together with scalar components and get that? So what we just saw is that 18 negative 2 is a linear combination of V and W. Because if I put a 1 out in front of the V and a 2 out in front of the W, I got 18 negative 2. And we also saw that negative 65, negative 72 is a linear combination of V and W. If I put negative 10 in front of the V and a positive 3 in front of the W, I get that. Okay. So this term, linear combination, is just referring to multiply of the two vectors that I've been given by scalars and adding them up. Combination means we're adding them up. Linear means I'm not multiplying by anything other than a real number or real numbers. Okay. Interestingly enough, every vector in standard position can be written as a linear combination of I and j in a very easy way. Okay. The vector AB can be written as A times I plus B times J. We understand why that is? Think about that for a second. Remember what I and J are. I is just 1, 0. So what we're doing is we're thinking of this as A0 plus 0B. This is A times 1, 0 plus B times 0, 1, which is A times vector I plus B times vector J. So every vector in standard form can be easily written as a linear combination of i's and j's. And if you're comfortable with that, then you can just use this form every time you're using a vector. The nice thing about this form is that now these i's and j's can be treated exactly like variables. That makes sense? So when we add them up, we're just adding coefficients together. Like if I add 5i plus 6i, that's just 11i. If we're subtracting, we can subtract just kind of like variables. So let me give you an example here. Let's say we know that V is a linear combination of I and J. V is 2I plus J. Now on my screen, that V is written in bold. So that I don't get thrown off when I'm writing things on the board, I'll switch to the arrow notation. Because it's hard to write bold stuff on the board. So I'll do this just because it'll go quickly. I don't think we need to spend a lot of time on it. Again, I've switched on the board to the arrow notation so I don't get confused between scalars and vectors, right? And it's easier to see, but obviously on the slide it was written boldface. When it says B minus 6W, we can take 2I plus J. Let's just set equal. Minus 6 times 5I minus J. When you distribute that minus 6, we get minus 30I plus 6J. And then essentially what I'm going to be doing in this notation is combining like terms. I's put together, J's put together. So we end up with negative 28I plus, looks like 7J. Same concept over here. We're going to do 5I minus J plus 7 times 2I plus J. 5I minus J plus 14I plus 7J. Again, and at this stage, I'm just thinking of combining like terms. Again, with this notation, this is very much like polynomial addition and multiplication and the distributive property of polynomials, things like that. Okay. So we get 19I plus 6J. And then this last one, we have I minus V. Now I'm going to do a distributive property right now, might as well. So I don't have to write another step. Is that okay? So minus V is minus 2I minus J. And then plus W. W is 5I minus J. Combining like terms, the i's together, that's going to be 4I minus 2j. So we have lots of different concepts of linear combinations coming through here. We have the fact that every vector can be written as a linear combination of i's and j's. And then we also have that this vector here, negative 28i plus 7j, is a linear combination of v and w. And 19i plus 6j is a linear combination of v and w, or w and v. Is that right? So there you go. Now I'm just going to note something on magnitude. There's a lot on this slide, but really the important part is this very bottom piece. Okay? Which says if you take the magnitude of a scalar times a vector, then that is the absolute value of that scalar times the magnitude of the vector. You can run through, that's what this line is. This is running through why that has to be the case. Okay. But if you take a scalar times a vector, then you distribute to C, then you have to find the magnitude of that. CA quantity squared plus CB quantity squared underneath the square root. This is going to be, I could factor out a C squared. Since it's under the square root, square root of C squared is the absolute value of C. So I can pull an absolute value of C out of that. And that is just the absolute value of C times the magnitude of the original vector. Okay. So in other words, if I know the length of a vector is 4, let's say, and I multiply that vector by a scalar of 3, then the resulting vector is going to have magnitude of 12. And it's also going to be in the same direction if I'm multiplying by a positive scalar. It's going to be the opposite direction if I'm multiplying by a negative scalar. Okay, follow that? So earlier we calculated that the vector 4, 3 had magnitude of 5. If somebody asks me for the magnitude of vector 12, 9, it's going to be 15 because 12, 9 is 3 times the vector 4, 3. Does that make sense? Since 12, 9 is 3 times that vector 4, 3, I know 12, 9 will have magnitude of 3 times 5, which is 15. And you can confirm that if you want to, but by calculating. Now, usually the way we use this tool is we use this tool to get unit vectors. I mentioned this earlier. I said we'd come back to it. We're coming back to it now. A unit vector is a vector whose magnitude is 1. These are nice because if we think about the starting point being the origin, then all of these vectors have terminal point ending on the unit circle. That makes sense. So vector is going to go from the origin off to the unit circle. And unit vectors are very nice, very useful in things. We saw two of these earlier, I and -1/2, comma √3/2. Those were both unit vectors. And if I have a vector in any direction, I can think of it as just a scalar multiple of a unit vector, no matter what the direction is. Let's say I have a vector of length 8 at angle π/3. Well, that's just the unit vector at angle π/3 scaled up by a factor of 8. Or let's say I have a vector of length 0.2 in the direction of 11 π/6. That's just the unit vector in the direction of 11 π/6 scaled down to a length of 0.2. Okay. Now, it's actually quite a simple process to figure out a unit vector in the direction of a vector v. If I want to figure out a unit vector in the direction of vector v, what I do is I just take the reciprocal of the magnitude of v as a scalar and multiply it times vector v. That has to have length 1 because of our previous slides. Remember the note on scalar multiplication and how that affects magnitude? Well, if I take the scalar 1 over magnitude of v, multiply it times vector v, and then take the magnitude, it has to be 1 over the magnitude times the magnitude, which is just 1. So if you ever want a unit vector in a certain direction, this is what you do. If you know the of vector direction you want to go in. So let's do that. Let's find a unit vector in the direction of these other ones. So we're going to find a unit vector in the direction of -6, 2. A unit vector in the direction of 0, 5. And then a unit vector in the direction of -3, -7. Okay. The first thing I'm going to do is I'm going to calculate the magnitude of this vector that I'm trying to find a unit vector for. 6, between -6, 2 is going to have a magnitude of square root of 40. I'll write all the steps. Yes, I did. +36 4 is 40, so square root of 40. That's an ugly thing, but that's all right. So the unit vector in this direction is just 1 divided by the square root of 40 multiplied times -6, 2. What we know about scalar multiplication is that it has to distribute. So we get -6 over square root of 40. And then 2 over square root of 40. You probably may ask for decimal versions of that. So you just type that in your calculator and get decimal versions of that. This can simplify if you want. I'm not going to simplify right now. It does simplify a little bit. But that's it, done. So to find the magnitude, then just multiply 1 over that magnitude by the actual vector. Here, the magnitude of 0, 5. We've done this enough, it's pretty obvious that that's 5. 0 squared plus 5 squared underneath the square root is just 5. So the unit vector in that direction is 1 over 5 times that vector. When I distribute this one, that's the vector 0, 1, or j. That one should have been fairly obvious and intuitive, right? 0, 5 is a vector that shoots straight up the y-axis. So if I want a vector of length 1 in that direction, I just need to take the vector 0, 1, shoot straight up the the y-axis. Let's do that over here as well. Magnitude of -3, -7. Calculate that first. Square root of 9 plus 49. When I square -3 and square -7. 9 plus 49 is 58. So we get square root of 58. That's not a perfect square, so I'm not going to simplify it. So the unit vector in that same direction is 1 over the square root of 58 times -3, -7. That's -3 over the square root of 58, comma, -7 over the square root of 58. Once again, you can rewrite that and simplify. If you want to rationalize the denominators, you can do that as well. But for me, that's good enough as it stands. Okay. You'll probably have to write a decimal version of those numbers on the test and on the homework. I want you to do the same thing that I just did, but with ij notation. So I want you to find unit vectors in the direction of these two given vectors. 7i plus 3j and 5i minus 5j.
Sorry.
All right. So let's go through this. I'll go quickly. 7i plus 3j is going to have a magnitude of square root of 49 plus 9, which is square root of 58. That means the unit vector is going to be 1 over the square root of 58 times this, times 7i plus 3j. If I want to write it like that, that's perfectly fine. I just have to distribute the 1 over square root of 58. And so the unit vector is 7 over the square root of 58 times I plus 3 over the square root of 58 times j. Same thing with this one, 5i minus 5j. We're getting the square root of 25 plus 25. So square root of 50 is the magnitude. You can simplify that. That's perfectly fine if you want. But I'm just going to take the unit vector, set it 1 over square root of 50 times 5i minus 5j. So we get 5 over root 50 times I minus 5 over root 50 times j. Okay. That would be the final answer. You'd write decimal versions on the test or whatever. I want to show you one little thing. Before I move on though, I want to simplify those numbers. Square root of 50 is 5 root 2. So this is like 5 divided by 5 times the square root of 2. I minus 5 over 5 root 2 j. 5s will cancel out. You get 1 over the square root of 2 times I minus 1 over the square root of 2 times j. And just so you know, another version of 1 over square root of 2 is root 2 over 2. That should look familiar, right? Root 2 over 2, negative root 2 over 2. That's at the 45-degree angles. We get those values. Or the pi over 4 angles, we get those values. Does that make sense? Was you? So I just point that out just to say, oh yeah, that's a known value on our unit circle. at 45 degrees or pi over 4. That's where we get that root 2 over 2 stuff. That would be in the first quadrant where both are positive. And second quadrant, you take 45 degrees plus 90, which is 135 degrees. And the third quadrant, 45 degrees plus 180. Fourth quadrant, 45 degrees plus 27. That makes sense. So that root 2 over 2 is the key. That's all I'm pointing out. Now, this kind of brings up one other thing. There is another way you can find unit vectors in a certain direction. And that is just to find the direction and then state, since each unit vector ends at the end point of a point on our unit circle, each unit vector can be thought of as cosine theta sine theta for some direction theta. So another way of finding the unit vector is to find the direction and then just plug in cosine theta is your x value, sine theta is your y value. Does that make sense? Let's do that with the previous scenario. Okay. We'll do it once each. So previously we had 5i minus 5j. And we found the unit vector. 1 over root 2i minus 1 over root 2j. You could have also found the theta by saying that the tangent of theta is going to be negative 5 over 5. You see what I'm doing there? Negative y value over x value. It's negative because the y value is negative. So the y value over the x value. And since this gets us into quadrant 4, the theta that I can use if I want to is just the tangent inverse of negative 5 over 5. If you type that into your calculator, you'll get a decimal version of negative pi over 4. So I'm just going to write this as negative pi over 4. So that we're really precise. And then the unit vector, I could have found by just taking the cosine of negative pi over 4, comma, the sine of negative pi over 4. You could have also written this in ij notation if you want. Cosine of negative pi over 4 times I plus sine of negative pi over 4 times j. Cosine of negative pi over 4 is root 2 over 2. Sine of negative pi over 4 is negative root 2 over 2. And like I said, if you wanted to write this in ij notation, as root 2 over 2i minus root 2 over 2j. That's the exact same thing we got the other way, right? Most people like this method better because it's a little more straightforward. In this method, you do have to worry about what quadrant you're in. So if you end up in quadrant 2 or 3, you have to add pi to that. And a lot of times, these theta angles don't come out nearly as nicely as in this case, like negative pi over 4. Okay. Let's do another one just for example. Earlier, we had negative 6, 2. And we used the magnitude to find the unit vector. It came out as negative 6 over root 40, comma 2 over root 40. That's what, if you remember that. Okay. That's how it came out earlier. If I wanted to do this, approach, I'd say that the tangent of theta is 2 over negative 6. We're in quadrant 2. So theta is going to be pi plus the inverse tangent of 2 over negative 6. And that's going to give me some ugly decimal. All right, I'm going to keep that in my calculator. It's about 2.82. And so another way to get this unit vector would be to take the cosine of that 2.82 number, comma, the sine of that 2.82 number. Now, I'm just going to do cosine of my answer. With all that. Cosine of my answer, so I'm not going to round it. That gave me about a negative 0.948678668, excuse me. 948. Let's just say rounded 4 decimal places that. And then if I take sine of that number, I get about a 0.3162. Makes sense. Now, if you would have calculated this unit vector, negative 6 over square root of 40, the decimal version of that, excuse me, you would have gotten the exact same decimal places. You would have gotten negative 0.9487, and then 2 over the square root of 40 would have been 0.3162. Does that make sense? So again, 2 different approaches. I tend to like the scalar multiplication approach to it rather than finding the direction, because with finding the direction, you have to be really careful about what quadrant you're in. I don't like that quite as much. Make sense? There you go. So I tend to use the scalar multiplication approach. So that's it for vectors. Which means that's it for chapter 8. We're going to move into chapter 9, which is systems of linear equations and matrices. These same concepts of vectors will be used with systems of linear equations, although in matrix form rather than the vector notation form. So we probably all know what a system of linear equations is. It's multiple linear equations. Okay. So there's an example. 4x minus 7y equals 23. Y equals 3x plus 4. That's two equations that are both linear in two variables. So this is a system of two linear equations with two variables. Okay. We're going to be looking for a solution to the system. A solution is a point that you can plug in to make both of them true. Now, if we have three equations, then it's a point that I can plug into all three equations and make all of them true. If I have four equations, then it's a point that I can plug into all four of them and make all four of them true. If I have two variables, it's an ordered pair. If I had three variables, it'd be an ordered triple. There'd be three, one value for each of the variables. And if I had four variables, it'd be an ordered quadruple. Most of the time in this class, we'll be dealing with systems with two variables. We'll deal with a little bit of systems with three variables. Okay. Now, one of the nicest ways to solve systems of linear equations, if we have two equations and two variables, is to graph the two equations. If you graph the two equations, again, this is only going to be working with two equations with two variables. Then I get two lines. And where those lines cross is going to be the solution to the system. Because each line represents all the points that make the equation true. So for a point to make both equations true, it has to be a point on both of the lines. And that's the point of intersections. Now, some weird things can happen with graphing. You might end up with two parallel lines, which means they never cross, so your system won't have any solutions. You might end up with two lines right on top of each other. In that case, there'd be infinitely many points that make both work. But the vast majority of times, you'll have one solution, and that's the point where they cross. Okay. Now, if you go and expand that out, that concept out, it actually works no matter how many variables and how many equations I have. We're always going to be in one of three situations. I'm either going to have a single point that works, which is the one solution case. Again, most of the time in here, that's the case that's going to happen. Or I'm going to be in the no solution case. Or my system is going to have infinitely many solutions. Okay. It's best visualized with two equations, two variables, but when you have however many variables, however many equations, it's still those three types of solutions. Okay. We'll look at three ways to solve systems of linear equations. We'll look at graphing. That's pretty straightforward. We'll look at using the elimination method. That's an algebraic method. And then we'll look at a substitution method. And then later on, next week, we'll see a method with matrices for solving systems of equations. So let's say I have this system, 2x minus y equals 5. And 3x minus 4y is equal to 10. And I want to solve this system via graph. Now, since we all have a graphing calculator, we can graph these two equations so long as we can put it into our graphing calculator. Putting this into our graphing calculator requires us to solve each equation for y. In other words, I need to get y equals something. So in this first equation, to do that, to solve for y, I would subtract 2x from both sides. That'll give me negative y equals negative 2x plus 5. And then divide both sides by negative 1. Which is y is equal to 2x minus 5. So I'm going to be plugging that into my graphing calculator. On the other one, oh, that was 3x minus 4y, excuse me. 3x minus 4y equals 10. I'm going to do the exact same process, but different numbers. So subtract 3x from both sides, and then divide by a negative 4. That'll give you y is equal to 3/4 x minus, that'll be 5/2 if you write it as a fraction. If you want to write it as a decimal, that's okay as well. That's 2.5 as a decimal. You could have also written this as a decimal. That 3/4 you could have written it as 0.75. Okay. By the way, don't round. Like 0.75 is the exact version. If you had 0.88888, don't round it to 0.89. That could really throw off where it hits. Once we have that, then I just turn to my calculator or other graphing tool. Again, I needed to solve and got y equals. Oh, I'm in still parametric mode from last time, so change my mode back to function in this case. So change your mode to function. Y equals. One of them was 2x minus 5. That is y equals 2x minus 5. The other was y equals 3/4 x minus 5 halves. You could have also written 0.75x minus 2.5. And then I'm going to zoom standard to see if I can figure out where those two lines cross. I can see that pretty easily. Sometimes it's kind of hard to see where that's at. If it's hard to see where that's at, just go into the calculate menu on the graphic calculator, and if you scroll down to number 5, you can find an intersection point. You just highlight what's the first curve you're given. First curve I'm given is this red line. Second curve, I'm going to choose the blue line. And then a guess, this just means get close to your point, then hit enter. This says that the point of intersection is the point where x is 2 and y is -1. So that is my solution to this system of linear equations. It's the point 2, -1. Be all right with that? So via graphing, I get that solution. Questions about that? It's pretty straightforward. So the graphic, see the solutions. Sometimes things can get hard to see on a graph if you don't have the right window. Imagine your solution is like 20, -35. You have to zoom out so you see where it hits, where the two lines cross. But other than that, it's fairly self-explanatory. We'll look at a couple of other methods as well. One method is known as the elimination method, or sometimes this is called the addition method. This is the method where we force opposite coefficients on one variable after we've aligned the equations up. So we're going to align the equations. Then we're going to force opposite coefficients on one variable. Then we're going to add the two equations together to eliminate a variable. That's why sometimes people call it the addition method. Sometimes people call it elimination, because you're adding two equations together and that process eliminates a variable. We solve for whatever variable remains. And then we plug that back in and solve for the eliminated variable. Now, the goal of the elimination method is to go from two equations with two variables down to one equation with one variable. Okay. That'll be a theme we'll do later when we get to three equations with three variables. Okay. I'll just do one of these as well. I'm sure you've seen this process before. we have this system of linear equations. 5x minus 4y is equal to -1. 2x plus 7y is equal to 34. Let's say we want to eliminate the y variable. That means I need to get opposite coefficients. One of the coefficients right now is the -4. The other coefficient is a 7. In order to get opposite coefficients, what I'm going to do is I'm going to take that -4, write it in front of the other equation. Then take the 7 and write it in front of the equation it's not in. And then I change the sign on one of those. So I'm going to eliminate y. In order to force opposite coefficients, I write coefficients of y in front of other equation. Then change the sign on one. And then I multiply through. Okay. And multiply. So I'm going to do 7 times 5x, that's 35x. 7 times -4y, that's minus 28y. 7 times -1, that's a -7. And I keep the equal sign in place where it's at. Then I multiply 4 into each term of the second equation. That's going to be 8x plus 28y is equal to 1. I think that's 36. I'm right. 4 times 34. Now we have a negative 28y and a positive 28y. That's exactly what we wanted. We wanted opposite coefficients so that on my next step, when I add them together, they get eliminated. When I add 35x and 8x, I get 43x. When I add the y's, they cancel each other out. That's why I wanted opposite coefficients. And then that's equal to 129. So now there's only one equation with one variable remaining. That variable in this case is x, so we solve for x. Pretty straightforward, solving for x. We got to divide both sides by 43. When you do that, you get x equals 3. Now, x is equal to 3 is not the final answer here. Remember, the solution to a system of linear equations with 2 variables is going to require 2 values. It's going to require an x value and a y value. So I need to plug that x equals 3 into one of these 2 equations. It doesn't matter which. I'll use the top equation. we get negative 4y is equal to negative 16. Divide by negative 4. And you get y is equal to 4. So now I have the solution. The solution is the point 3, 4. Right. That's our elimination method. On 2 variables. Now, I'm only going to do one example of this because, like I said, later on, we'll see other ways of other methods of solving linear equations like this, systems of linear equations like this. If you want to see more examples, there is a video out there of all of the examples in this section, so you can check that out if you like. But for right now, I'm only going to do one example of each of those 3 methods: the graphing, the elimination, and the substitution method. Okay. So that brings us to our last method, which is substitution. Substitution works when we have one equation that's written as a variable is equal to an expression with the other variable in it. Like y is equal to 2x plus 5. Or y is equal to 3/4 x minus 7. Or x is equal to 2y minus 3. Something like that. If we have that scenario, then we're just going to substitute out the expression for the variable in the other equation. That's going to get rid of the variable in my other equation, which means I now have an equation with just only one variable in it. So I can solve for that variable. And then I'll plug that number I get out into the very first equation to solve for the other variable. Again, it's easier done than said sometimes. That makes sense. Might be confusing trying to figure out, well, which ones are remaining, which ones are eliminated. Well, it's going to be obvious when you go through that process. Again, the goal is to eliminate one equation and one of the variables. So let's do an example. Here we have y is equal to negative x plus 8. And then 2x minus 2y is equal to 6. This one is set up for us to do substitution. It's set up that way. I know it's set up that way because we have y is equal to an expression in that first equation. So first equation, we have what we want. So what we're going to do is we're going to replace the y with the expression negative x plus 8 in this second equation. So we replace the y with negative x plus 8 in that equation. That'll give us 2x minus 2 times negative x plus 8 is equal to 6. That's an equation with one variable, so we can solve for that variable. The variable here, once again, is x that is remaining. Everybody see where I got that? Straightforward. Good. So we have 2x. This will be plus another 2x minus 16 is equal to 8. I will add 16 to both sides. I misspoke. I wrote the correct. So negative 2 times negative x plus 8 is 2x minus 16. That's equal to, the left-hand side is equal to 6. On the right-hand side. I will add 16 to both sides, giving me 4x is equal to 22. Then I would divide both sides by 4. Depending on how you like to write your answer. If you like to write your answer as a improper fraction, it'd be 11 halves. If you wanted to write your answer as a decimal, it'd be 5.5. I think I'll leave it as a decimal right now. So we get x is equal to 5.5. And then we plug that in. To one of these two equations. Now, it doesn't matter which one, but it'll be a little bit easier on me if I plug it into the first one. So, y is equal to negative 5.5 plus 8. There's really only one step to do if I plug it into the first one. There's going to be a couple of steps if I plug into the second equation. So y is equal to, that's 2.5, isn't it? 2.5. So now I have my solution. My solution as an ordered pair is x value 5.5, y value 2.5. So that ordered pair is my solution. Any questions about that? That material, that's pretty straightforward. Good. Now, there are some weird things that can happen either with elimination or substitution. I'll do this example really quick. I know I said I do one just of each, but this is an example that has a weird scenario in it. Here we have 2x minus 6y equals 4, and x is equal to 3y plus 2. So it's set up for us to do substitution because the second equation has an x equals an expression. So what we're going to do is we're going to replace the x with 3y plus 2 in the 2x minus 6y equals 4 equation. If I do that, I end up with 6y plus 4 minus 6y is equal to 4. Is that right? 6y minus 6y gives me 0, and I'm left with 4 equals 4. So my variable has dropped out. And what kind of a solution is this?
The infinitely many.
This is the infinitely many solution scenario. If my variable drops away and I end up with a true statement, it's infinitely many solutions. By the way, if we would have ended up with like 4 equals 10, we would have ended up with a no solution scenario. Okay. If your variable drops away and you get a false statement, then it's a no solution scenario. All right. We'll pick back up here next class. Remember, no class Thursday. You will still have to do the homework up to 8 a.m. All right, up to the vector stuff. So vector stuff, that stuff will be due on Thursday, and then this stuff will not be due yet. All right, I'll see you next time. Have a happy Thanksgiving.